The maths of gravitational fields isn't really any more complicated than anything we've met so far, but they are slightly awkward things, because gravitational fields, or fields in general, because they are what's called an abstract concept. So let's just imagine E10 in work. We know that gravity, just like any other room on Earth, is acting down like this, isn't it? And that as a result of the gravitational field in the room, any object placed in the room, I don't know, like the PC on the front desk, will then feel a force or a weight acting down due to that field. And it becomes almost a philosophical question. At this point here in the room where there is nothing, is there a gravitational field? And the answer, as far as modern physics is concerned, there is. So everywhere in the room is a field. It's uniform because the field is the same everywhere. In other words, the weight of the computer is the same wherever we put it in the room. And we represent uniform fields by these parallel straight field lines. And we know that the field strength in the room, G, is 9.81 newtons per kilogram. We also know that G is 9.81 meters per second squared. So that's the acceleration due to gravity. But this one here is the important one today, because that's the field strength. And there are not vast numbers of quantities in fields, but just keeping track of what they all mean is absolutely crucial. So field strength, the amount of force per kilogram. Look at the units and remember that. So what's the equation for field strength? So field strength is simply force per unit mass. So the force of gravity divided by the mass of the object in the field gives us the field strength. So let's just do a kind of crazy simple example. We zip off to a new planet and we take with us a 10 kilogram mass, and we're standing on the planet with our 10 kilogram mass. We have a kind of force meter here, and the reading on the force meter is 30 newtons, and therefore we know the field strength on this planet is 3 newtons per kilogram. We can also come up with quite a simple universal equation for working out what the field strength is on a new planet. So we've got F equals G M1 M2 over R squared. And I'm just going to draw a little picture. Let's make M1 the mass of the planet and M2 the mass of the object kind of on the planet. We know, don't we, that G equals F over M, and it's going to be M2 in this case because it's M2 that we might be measuring the force of gravity on, like that picture there. So we get G M1 M2 over R squared times by 1 over M2. I mean, that's me dividing by that M2. So we get the force of gravity due to an object mass M, that is a distance R away, is Gm over R squared. You can have a go now at doing some questions. I'm just going to point out one thing that crops up in the next lot of work that's kind of important to get your head round. Usually, the way we imagine you and the work interacting with the Earth is we say, well, the Earth has a gravitational field, which we can draw as this radial field. Now, that's worth just doing that. As you can see, as we go further from Earth, the field lines are further apart, aren't they? So that indicates that out here the field is weaker, and the equation says the same thing. So this isn't a uniform field, and because all these lines are heading towards the centre of the Earth, this is called a radial field. So the normal way of regarding you standing on the Earth is the Earth very large massive object creates a very strong gravitational field. You're in that gravitational field, and as you're in that field, you feel a weight pulling you down. But of course, we can make it much more kind of John-centric, or whoever you are centric. And we can say that you create a very weak gravitational field, and it is the Earth that is caught in your gravitational field, and you're pulling on the Earth. But because your field is very weak, doesn't have any newtons per kilogram, because there's a lot of kilograms in the Earth, in both situations we get the force of gravity on you as being exactly the same.